I want to welcome everyone and thank you for joining today's webinar, Exploring ROI of Optical Spectroscopy for Inline Moisture Measurements in Process Manufacturing. This webinar is co-hosted by ISA, Helmut Analytics, and Process Technology. I'm Michaela Cooper with ISA, and I'll be hosting today's webinar. Also with me today, I have Krista Shepard with Process Technology, who will be moderating today's webinar. But before we get started, I'd just like to review a few housekeeping items to let you know how you can participate in today's webinar. First, in regards to the question and answer session, as well as the poll sessions, we do have one poll question in the webinar. And when the poll question pops up, we ask that you enter your poll answer into the poll feature on the WebEx navigation, which is on the right-hand side of your screen. And this is completely anonymous, so no other attendees can see what your answer is. So feel free to join in and engage with us today in the poll question. Also, we do have two Q&A sessions within the webinar, one kind of halfway through and then one at the end. And to submit your questions, we ask that you type them into the Q&A chat box on the right-hand side of your screen. We ask that you do not use the chat toolbox for the Q&A session, so that way we can keep all the Q&A questions all in one area. And if we do not get a chance to respond to your question, or if you would like to discuss a topic in more detail with one of the presenters, we will provide their contact information at the end of the webinar. And second, for those of you who just joined, please make sure you are on mute. We want to be respectful to the presenters. If you'd like to see the phone and audio broadcast connection instructions again, please refer to the confirmation email I sent to you, or if you go to the top left-hand side of your WebEx screen, you'll see a tab labeled Event Info, and some of those connection instructions are included there as well. Additionally, once this webinar closes, a survey should pop up in your browser. And we ask if you just take a few minutes to answer the survey. It's really short, just a few questions. We want to get your feedback to see how we can make these webinars better for you, our audience. And to make sure everybody is aware, ISA-sponsored webinars are educational offerings with no direct promotion of proprietary products or services. Consistent with the non-commercial nature of these events, participation of the independent subject matter expert is to add further technical knowledge and is not an express or implied endorsement of the sponsor or the sponsor's products, services, or representatives. Okay, now I think that takes care of some of the housekeeping matters. Now to introduce our first presenter, Robert E. Bob Sherman, a principal technologist. He has worked for major companies such as BP, Valero, and Fluor in both North America and overseas. He has over 40 years of practical experience in the field, solving sample conditioning and analyzer application problems. He has been an ISA Fellow since 2002. He's an author of Process Analyzer Sample Conditioning Systems and an editor of ISA's Analytical Instrumentation of Practical Guide Series volume. Next, we have Navin, an application scientist with Process Technology. He holds a PhD in biological engineering with specializations in chemical engineering and chemistry from Louisiana State University. His doctoral accomplishments at LSU were recognized by the Oak Ridge Institute for Science and Education and earned him the ROI Research Fellowship to develop rapid spectroscopic screening techniques at the U.S. Food and Drug Administration. And last but certainly not least, we have Stacey Carrier, Technical Sales Manager at Helmut. She holds a PhD in physical chemistry, specializing in reaction dynamics in UV, VIS, and mid-IR spectroscopy. Provides technical expertise and scientific knowledge to determine best sample interface for inline measurements. Has accomplishments that include a thorough background of optical spectroscopies and instrument design. We have a great panelist today, and Right now, I'm going to kick it off to Krista Shepard, our moderator, to go over the agenda and kick off the rest of this webinar.
Hi, everyone. Today, we're going to start by talking about the various moisture methods and technologies and looking at comparing offline versus online and inline measurements. As Michaela talked about earlier, there will be a quick poll that will come up on the screen, and that poll will run for the entire session, and we'll go over that poll at the end. We'll have a Q&A session, and then we'll dive into inline spectroscopy specifically and how that solution works. What do you need to know about an installation and the integration issues? What's the cost of ownership? What it takes to the calibration, and then we're also going to look at some case studies and then talk about the overall ROI. So to get this started, I'm going to turn this over to Bob.
Good morning. Does measuring moisture matter? Yeah, it's important in virtually every industrial manufacturing process. Actually, if moisture wasn't necessary for human life, it would probably be considered a hazardous substance. And anyone out there that has tried to do parts per million or parts per billion moisture measurement understands moisture's extreme attraction for surfaces, metal surfaces, glass surfaces. It's extremely difficult to break the bond of the last molecules of water adhering to surfaces, and that will affect some of the measurements that we're going to talk about today. Moisture also impacts shipping weights, performance characteristics of reactions, process parameters, and the final cost of the product. Performance characteristics, if you store powders with moisture in them below 32 degrees Fahrenheit in storage or shipment, it can damage the performance of the powders when you go to mix them into your products. Also, neither manufacturers nor consumers want to pay extra for extra grams of water coming along with the product that they're paying for. Shelf life. If there's extra moisture over the amount needed for the initial reaction in a product, oftentimes there's continuing reaction within the packaging of the excess water that's present. To stop the susceptibility of further reactions, once again, if excess water is present there, then the reaction will continue to occur even though the standard reaction has ran to completion for developing of your product. Consistency of the product, this influences customer loyalty, and we all know, whether we're engineers or in product sales, that customer loyalty is the continuing lifeline of your business. Common moisture measurement methods: offline, typically laboratory. Karl Fischer titration, loss on drying. Comments on Karl Fischer titration: it can be either coulometric or volumetric. It has a tendency to drift. Initially, you'll get the reaction with the Karl Fischer reagent of the water in the material. But then if it's a high level of water, there will be water get out on the vessel walls like I just spoke of before, and that will introduce drift into the measurement as the reagent scavenges the last bits of water off the walls. The reagent in Karl Fischer is noxious. It smells fishy. It's pyridine, and it's not very pleasant to handle outside of a hood. Anything that is to be measured via the moisture by Karl Fischer, the entire sample has to be methanol soluble. And when you finish the reaction of the Karl Fischer and determine your moisture level, what you have left is a hazardous waste, and you have to pay to dispose of that. Loss on drying. Here we're talking about just thermal ovens, but you need the space for the ovens. They're not miniature. They have to be, to hold the temperatures, they have to be fairly large, well insulated from the ambient temperatures, changes in the room. The Power for the ovens, the electricity to run the ovens. You know, you're continually running the oven to hold it at a given temperature, and then it's emanating heat through the insulation to the room, so you're running the air conditioning to counteract the ovens, and you're running the ovens. You're consuming electricity at all times. Also, with loss on drying, you're not only measuring the moisture that is leaving, but any volatiles that have a ability to evaporate within the temperature range that you're using for loss on drying. Inline, this is the process measurements. Basic is conductivity, used in salt removal processes. You have both anionic and cationic conductivity. Some people may refer to it as resistivity. Conductivity is defined actually as 1 over resistivity. It's usually a simple probe into the process, but it can foul. You need to either remove it to clean it, or you need to clean it in place. Microwave. This is usually used for a bed of powder passing beneath a sensor. And you have heating of the matrix. Once again, the microwave heats the moisture and gets it to go out of the matrix, but also other volatiles that may be affected by the microwave, will disappear from the process and give you a false value for actual loss of water. Inline optical. Here we have photometry and spectroscopy, and maybe people think, well, these are both 3 boxes, a light, a cell, and a detector. But photometry formally is defined as, an overall measurement of light, concerning on the product or the reaction. Easiest one to think of here is opacity. It's just a matter of smoke in a duct or material in a duct will remove some of the light going through the duct. Photometry typically does not need a model to be developed to give information. Spectroscopy, this is more discrete considerations. It focuses on a specific band or a specific molecule. You get much more info about that molecule, but to get that more info, it requires more calibration. Typically, you have to build a model to get the most benefits out of spectroscopic measurements. Okay, here we've arrived at the pole, and just what we talked about. We'd like to know what our audience, what kind of moisture measurement they're currently doing. And you can fill out more than one. If you have a laboratory that's doing Karl Fischer, and an inline doing photometry, and then an inline FTNIR or laser spectrometer that is doing spectroscopy, fill this out. If we bring up something that during the rest of the talk, and we got one of those out there in the plant, just fill it in. We will check these at the end and discuss them. Okay, back again, Karl Fischer titration. We've provided you some more detail here besides just what I talk about, but the method measures only water content. It's water specific. Once again, the reagent is noxious. It's pyridine. It converts water to a non-conductive chemical. You have iodine also involved in the reaction. Just like more people are becoming allergic to peanuts and shellfish, there are people that have iodine reactions, adverse reactions to iodine also. Once again, water is difficult to separate from a sample. An example of that is measuring moisture in chocolate. You chop up the chocolate, and even if you chop it up very finely, it does not, moisture does not leave the matrix of the chocolate easily, and it takes a long time to make this measurement. Once again, water is difficult to release from the reaction vessel or reaction container surfaces, so you get drift of a final measurement, and you in general have to do a blank with the material that you're interested in, and see what the length of time to get to a final endpoint is. and then you subtract that long drift if it's acceptable from your value that you do in a timely fashion. Loss on drying, again, total change of weight is water plus volatiles. And you need to know somewhere what your volatiles are, what the temperature is that they will go off from the product, and the matrix of the product has to be continuously the same of water and volatiles, or else your values that you get will not be representative of water in your product. And the loss on drying is the difference in the weight, and you assume that the loss of weight is the percentage of moisture in the product, but it's not necessarily. It could be the percentage of moisture plus volatiles in the product. Benefits of offline methods, they can be accurate, they're widely accepted, there's a lot of procedures written for them in detail. They support the laboratory that is required for other considerations, and the technicians perform the offline measurements based on long historical usage for comparison to process values for producing your product. Limitations, trained labor, people doing the offline methods, you have human error, and it's not necessarily intentional. It's that one person's vision or color consideration of his vision or her vision may be different than another technician's vision, whereas the inline spectrophotometer measuring color measures the same every time. Also, sample extractions and the transportation of these samples can change their values. One person takes a sample off of a pipeline under high pressure into the sample container that he's going to transport it to the lab, and this high pressure will cause low boiling materials to fractionate off and be lost. Other people, may take a grab sample, and if they're taking it from a tank or a open container of liquid, if it has sat for a while, you may get stratification. So one person dips just at the surface, one person dips at the way down at the bottom of the container, and those samples will measure different, when the analyst does them in the laboratory. You've got to support the lab space. It's got to be comfortable for the technicians to work. Also, as we mentioned about the ovens before, you've got to keep the lab at a pretty constant temperature, so the ovens stay at a constant temperature. That's going to require power for the ovens, power for the air conditioning. Reagents to perform the measurement, you've got to have reagents. If you only perform the measurement occasionally, you open reagent, especially like the Karl Fischer materials, they take on water from the atmosphere, so in humid areas, you may have to throw away reagents that you just opened up and use a new one for the next reaction measurement. They're time consuming, the results are not immediate. Again, we were talking that your Karl Fischer has to proceed slowly, and then if it's a high moisture value, you've got the moisture on the walls of the vessel. You've got to titrate that off of the walls of the vessel, and that tails out. So your initial reaction may be 5 minutes, but you may have a 15-minute tail on it that you have to then factor in. If the tail is the same all the time, can you really only run the reaction 5 minutes? And it destroys the samples. It changes the sample. And once again, that creates hazardous waste that you've got to handle, dispose of, and in general pay for the disposal of. Conductivity, it's a measurement of how a specific material conducts electricity. You can measure capacitance, conductance, or resistance of a material. They're all in general referred to as conductivity measurements. The purer the water is in your product, the poorer the conductor is, and the less reliable the value is of the conductivity measurement you're making. Matrix changes that react differently to electricity can affect the values of water that you're measuring via conductivity. Microwave, once again, typically this is a microwave over a bed of powder or web of some sort that you want to know a constant moisture level in. Water is an excellent absorber in the microwave region, so it absorbs energy and can be measured or can be driven off, to dry to a certain level. Also, water absorption can be used to quantify water concentration. The benefits of conductivity: it's inexpensive. It's typically a small probe that's inserted into a line. Low power requirement. The conductivity analyzer is not a major consumer of power. It's easy to use, whether it's in the lab. It's essentially a probe that goes into a vessel that is stirred, and it can be portable. The measurement can be taken to the field, instead of inside the laboratory. Limitations: the conductivity is blind to changes in the chemical makeup of the solution or the background matrix of the product. High maintenance: the probe requires frequent replacement. The probes are several $100s a piece, and you've got to run a standard on them and then replace it if the probe doesn't meet the consideration. Detection limit is 30 to 40% of water content. It'll go down low into the low percentage, high part per million, but you've got limits there. The moisture becomes more inaccurate, again, because of the tailing consideration and wall effect, less than 4 or 6% of moisture or water. And sample density and temperature: once again, your matrix of the product affects the measurements by conductivity. Microwave benefits: can detect moisture at the surface or into the core of the product, down lower than the surface of a powder or granular bed or a thin sheet going by. It measures a small area where the microwave beam is impinging on the product, so you're taking a small area, assuming it's representative of the large bed of product. Sensors can be installed directly on the production line. The powder's passing below it, or a web is passing below it. You may want to put multiple sensors across an array of sensors and average them to get a better value of offline moisture measurement. Limitation: it needs a dryer before the measurement to drive the moisture off, and then you're only measuring, you're not driving moisture off or consuming moisture, you're just measuring what is left in your product. Used often on conveyor belts. It's not applicable to liftwoods. It's dependent on the electrical consideration, permittivity of the analyte. It can be limited by temperature, and analyzing time is greater than milliseconds. So if the bed or web is moving fast, you may not get a valid analysis. Inline optical methods: photometers, again, measures the overall magnitude of all the light. Spectrometers spatially disperses different wavelengths of the light, and you select one of these wavelengths to impinge on the product, and you get a discrete value for that analyte from that discrete wavelength of the spectrometer or spectrophotometer. Benefits of photometers: they require less calibration. They're non-destructive. They can be tuned via their full intensity for specific applications. Applicable for solids, liquids, powders. They're low power. They can be portable. Don't require a model built up, and cost lower than a spectrometer. The limits: they will not work for applications that require different wavelengths. If you have different materials in your product, they may respond differently to the photometer. They are only good for applications where chemistry, the matrix, does not change over time. typically only one parameter is measured, but they can be expanded to 2 or 3 parameters, and they need to be initially calibrated with a pure material and then pure plus a known spike to get multiple components there. Spectrometers or spectroscopy, they monitor the reaction in real time. The acquisition cost has came down dramatically, and no longer every spectrophotometer that you think of is $200,000 instrument. They have an extremely low cost of ownership. About the only thing you have to do is change out the source. It used to be monthly, and nowadays it's 1,500 hours, 2,500 hours. They can be used for solids, liquids, and powders by limiting the thickness of the material that you're passing the beam through. With Chemometrics, they can measure complex chemistries. You can get multiple measurement parameters, again, with software, the Chemometrics. They're non-destructive to the sample. They measure in milliseconds. Low power, they can be portable, but in general, they're mounted at the process. Limitations, the instrument choice, you have to select an IR, an NIR, VIS, UV, far UV. My colleague will cover the considerations of this in depth. And the spectrophotometer needs to be initially calibrated, typically against a primary standard or a primary method for the analyte or analytes of interest, again, if you delve into the Chemometrics. Any questions now?
Okay, so this is Krista, and if you have any questions in the bottom right-hand side, you can type in the Q&A, and then we'll read the questions. In this first section, we'll spend about 10 minutes answering the questions, and then we'll move on to the second session. Okay, so the first question that has come in is, what are relative startup costs for offline versus inline?
The offline is the laboratory, the training, the on benchtop analyzer, reagents, continuous, versus the inline. This is the cost of putting the spectrophotometer out somewhere near the line. You don't have reagent considerations, you don't have operator considerations, and more so now, and we will see this as we get further into this presentation. It used to be that you had to worry about making the spectrophotometer meet electrical hazard considerations. It had to be explosion proof, it had to meet NEC, National Electric Code, it had to meet NFPA, National Fire Protection Association. That's no longer true. Nowadays, you can take fiber optic cable, and fiber optic cable will allow the spectrophotometer to be placed back in a general purpose area, and you can run the fiber optic cable, an existing cable tray, or other means out to the probe that is in the process. The fiber optic will transfer the source energy into the probe. You will have a gap in the probe. You will have a sensor where the material in the reaction that you're looking at takes away some of the light intensity, and then the remaining light intensity is transmitted via a second fiber optic cable or a second strand in a one fiber optic cable back to the spectrophotometer in a safe area. And like I say, they can become quite cost effective, as inline spectrophotometers versus new laboratory benchtop ran by operator tests.
Okay, and some of the other questions that are coming in right now, I think we're going to hold those until the second session Q&A, because we're going to cover a lot of these answers in the back part of the presentation. But one other question that came in, are all inline solutions extremely expensive?
Once again, the consideration that the inline solution If you have to put the spectrophotometer out by the process piping, number one, it may have to be made electrically hazard. You may have to meet electrical hazard considerations. That is usually an expensive process. You may have to package it and put a purge on it to meet the electrical considerations. Then you've got a problem of, if you ever need to work on it, you've got to make sure the area is safe. You've got to bypass the purge and maintain power on the analyzer. Some of these spectrophotometers are sensitive to temperature, so you still may have to put them into some kind of enclosure or put some sunshade over it, especially in the southern U.S. Impinging sun on a spectrophotometer case, you can hit 160 degrees or so inside that spectrophotometer case in the summer. And then in the winter, you've got to have a heater in there. What you want ideally is you want the spectrophotometer to be at the same temperature year-round. So you may heat it in the winter to 100 degrees Fahrenheit and cool it in the summer to 100 degrees Fahrenheit, cooling it down from 160 to 100 with some technology, a vortex tube or a mechanical chiller, or heating it with, once again, either a general purpose, depending on where your consideration is for electrical hazard, or an explosion-proof heater. And again, you need to keep the temperature, constant. So not only do you have to have the heater and the air conditioner, but you've got to have something in there that's going to move the air around to keep the temperature constant on the body of the spectrophotometer, which keeps the electronics and the optics at a constant temperature.
Okay. So now we're going to move on to the second session, and Stacey Carrier from HOMA is going to start explaining to us how an inline spectroscopy solution will work.
Thank you, Krista. Thank you, Bob. So when you first start looking at a problem, a lot of times it will be like finding a needle in a haystack, and you want to know one or two results or one or two values in which will tell you, hey, this makes our process good, this makes our process bad, doom. So what you have to do is, first of all, you have to find that haystack in which will give you the results that you want. And so we've gone over some of the offline inline methods, but today, as our title suggests, we're going to focus on spectroscopy. So let's give everybody a little introduction to spectroscopy. Spectroscopy is the measurement of the interaction of electromagnetic radiation with matter, okay? In most people's world, it means the measurement of light, okay? Because, well, not many of us deal with gamma rays or X-rays or whatever. And as you see in the graphic below, you'll see that usually you have this entire range of electromagnetic radiation, but we usually focus on the UV vis, near IR, and occasionally the mid-infrared regions, which will actually tell us a lot of information about the chemical structure, about your entire solution, about your entire matrix. Within this presentation, you may hear us use certain terms like wavelength, wave number, frequency. All of that will just tell you a little bit about the energy of the light that we're working with. Okay, so how the science works. First of all, so spectroscopy is the measurement of light for our purposes, and the first thing you have to do is you have to shine the light onto your sample or through your sample, and you need to be able to pick whether or not you are going to use UV light or visible light or all the way through the infrared by figuring out what you're actually trying to measure. So you have to pick the right wavelength region for your task. And the second thing is that when the light actually hits the sample, the molecules within the sample are actually going to interact, and they're going to absorb or transmit certain regions of light, which allows us to detect what is not absorbed or absorbed. And so this allows you to give a spectral fingerprint that can be used for real-time analysis. Now, we are going to actually focus on near infrared because water absorbs light really, really well from the near IR to the mid-IR regions with many strong, distinct features. Okay, so the big question is also, why would you want to even measure with light? Well, first of all, it's non-destructive. It usually does not destroy the sample that you're working with. It's very, very fast. You can take the measurements within milliseconds. It is very low maintenance. So you have limited sample prep and really no consumables. So the last two things is that it's very accurate and precise, especially when it comes to measuring molecules and matrices. And finally, it reduces costs. You don't have to it's not labor intensive, it doesn't create a lot of waste, and you can measure things in real time. Okay. Another reason is that spectroscopy is a proven science. It was first discovered in the late 1880s, and it became extremely popular for lab measurements. I don't know about any of you, but I know that all undergrad chemistry students use UV-vis measurements. I mean, UV-vis instrumentation is very widespread. The difficulty is that it's potentially fragile, it's sensitive, it can be manual, and a lot of times a scientist is required not only for the initial prep, but the instruments analysis, but you also have the after analysis required. But there are now ways that you can actually put this into process, and in order to put this into process, you have to make it rugged, versatile, everything. It's usually helpful if everything is in one box, because then you're not taking up huge amounts of space. You want fairly low cost of ownership, fully connected to everything, and very robust measurements. Okay, as I said before, we are actually going to focus on near IR for moisture measurements. Now, near IR is often used in powders and liquids, and it will go into the parts per million range for detection limits. Mid-IR is less frequently used. You can actually get to the parts per billion range, but there are several technical difficulties that arise when you try to go to mid-infrared, and so it's usually only used when you're trying to measure moisture in trace amounts of gases. Okay, so this is just a small example of a moisture measurement where you can actually see the visible and near infrared, the raw spectra of water and red wine, and you can see the water bands that are being pulled out of the wine, and you can actually just tell the difference, and from those differences you can do an analysis. Okay, so how does this work? Classically, what you do is you take light, usually it's a broadband light source, you throw it through potentially a filter, and then you take a monochromator where you've split up the light into its discrete little wavelengths. And then you send that light through your sample and potentially reference to hit your photodiode or your photodiode array. And then you can do some data processing and you can do some readouts. But in order to take this into process, it's not very handy in order to take the sample cuvette and pipette something out of your system, put it into your cuvette, walk over to your instrument, and then take a measurement. You want to be able to do this in line. And so in order to do this in line, you can use something like an immersion probe or a reflection probe or something like this. So rather than using a sample cuvette, where the sample cuvette is going to go, we're actually going to replace that with a fiber optic immersion probe. And that immersion probe is basically a portable cuvette that is connected to the instrument using fiber optics, which the fiber optics are basically like long snake-like objects that transmit light from the spectrometer to your process. And these can be anywhere from as short as you want to, it can be 50, 100 meters away, depending on your wavelength range. So it means that you can take your instrument, put it away from your process, and still measure your process in line. Okay, so there are several different types of interfaces for the sample measurements that you may want to consider, because whether or not you're dealing with a solid or a liquid sample, you know, your interface will change. Now, for a solid sample, you usually use what's called diffuse reflectance, and you basically, it's bouncing light off the surface and collecting light, basically coming back into your sample probe. And this you can work either contact, which means that you can take this probe and jab it into incoming samples to measure water content, or you can have something set up on a conveyor belt and have a distance measurement that allows you to take the reflection off of a conveyor belt of potentially like grains going through, you know, certain testing. So, and one unique setup that I've seen in the past is that for transparent samples such as glass, you can actually measure both the reflection and the transmission simultaneously. So you would have a reflection probe and something else collecting the light on the other side. You can do that simultaneously, and it actually gives you much more precise data if you have this transparent samples. But most people, when they think of probes, is they think of liquid and gaseous samples. You want to be able to take this probe, stick it into your beaker or into your process line. And so first of all, you have several different types of measurements. First of all, you have what's called a transmission probe, and it's a single pass probe that is most analogous to a cuvette, where the gap between the illumination and the detection side of the probe is basically like each side of the cuvette. Now, a transflection probe is a double pass probe where you would actually put a mirror on one side of the probe, and so you would actually bounce it on the mirror and pass it through the sample a second time. So you basically have an optical measurement thing twice the path length of the mechanical distance. Now, both of transmission and transflection probes will have path lengths usually about 1 to 20 millimeters. But the third thing, and this is called an ATR probe, is for samples that will give extremely, extremely high signals. And so what you do is you have a potentially like a 3-ounce crystal where it's actually measuring just at the surface of the crystal. And this allows you to have path lengths on the order of the wavelengths. And so for highly absorbing samples, usually one will go to an ATR probe. Okay. So a few examples of some inline sample interfaces, and these are what you can stick directly into your pipeline, as shown by the picture of that guy staring intensely at the probe. But it allows you to actually connect your probe into your pipeline and measure things as it's flowing through. Now, we did tell you that spectroscopy, you can take things in milliseconds, which allows you to have real-time analysis of your materials. Now, the great thing about these sample interfaces is that they can be made of a huge array of construction materials. So, you know, you can make it out of stainless steel, hastelloy, titanium, Teflon, sapphire, quartz. So there's this huge range of materials, and some of the examples shown is that you can have something made out of PTFE and sapphire. So it's this extraordinarily chemically robust probe that you can put into very strong acids. We also have shown is an all-quartz probe where not only is the probe made out of quartz, but the entire flange is also made out of quartz. And this was created for something where absolutely no metal whatsoever could have been in the process. So this was a very specialized thing, but it shows some of the versatility of what an immersion probe can be. Okay, the other thing that you can do is with sample interfaces is that you can have flow cells. So if you have a pipeline and you want to put basically probes on each side of the pipeline, then you can basically insert those into a flange, insert that into the pipeline, and as this is going through, it's just literally passing through the illumination and the detection probe. You can also have certain bypass mechanisms that allow you to take off small samples and flow it through a smaller type of flow-through cell. So you can, if you can't have a probe in a certain area, you can have a small bypass loop, which is a very common methodology. Okay. And with that, I am actually going to pass this off to my colleague, Navin.
All right. Thank you, Stacey, for explaining the pros and other engineering stuff about spectroscopy. And hello, everyone, and thanks for your interest to our webinar on exploring the return on investment of inline optical spectroscopy for moisture measurements. So before I move on to my part of the webinar, I would like to briefly highlight the sessions we have had so far, which included discussion about the existing methods used to measure moisture in industrial processes, as well as the engineering and science behind the use of optical spectrometers to overcome the challenges imposed by these techniques, such as Karl Fischer, loss on drying, microwave, to name a few. So from this section of the webinar, I will be talking to you on how to extract real-time information on the manufacturing processes using inline optical spectrometers. So this section or session will help you to understand on how to analyze the moisture content based on the spectral data acquired during the manufacturing process, although other types of measurements can also be investigated. So to begin with, I would like to introduce chemometrics techniques. And for those of you who are new to chemometrics, a simple way to define it is it's a mathematical technique which uses statistical models to analyze chemical data quantitatively and qualitatively. So the key to chemometrics is not understanding the mathematics of all the different methods, but to know which statistical model to use for any given problem. The data that's generated by modern optical spectrometers produce large and huge quantities of numbers, which requires every spectroscopic scientist to use computers to process the complex spectral information into reasonable and simple results. There are many algorithms which are available to analyze the spectral data. However, we will not dive into those details since there are various chemometrics software packages available, which really eliminates the task of writing long algorithms to interpret the spectral results. So most of the trained spectroscopists have a basic understanding of the concepts that's really necessary to apply these statistical models for data interpretation. For example, in this slide 35, top left image shows a raw near-infrared spectra of the same sample with different moisture levels. These spectra might make no sense at first to someone who wants to quantify the moisture content during a manufacturing process and probably be unrealistic to interpret the results since these spectra have different baselines and absorption intensities which can be attributed to instrumentation parameters, sampling properties, etc. Or to put it simply, these spectra might look nothing more than a squiggly line for a novice spectroscopic user. However, as I just mentioned a couple of minutes back, these spectra can be treated mathematically to convert them into valuable and reasonable results. As an example, the image on the left bottom of slide 35 shows mathematically treated or mathematically pre-processed near-infrared spectra for the results shown in the left-hand side top image of the same slide. So this mathematical pre-processing was carried out using our commercially available Chemometrics software package, and the pre-processing steps included for this mathematical treatment was second derivative and standard normal variate methods. So once the mathematically pre-processed spectra is obtained, it can now be used to build a model, a statistical model, of course, which can be used to predict the component of interest quantitatively. But before a spectroscopist can build such a model, like the one shown on the right-hand side image in slide 35, he or she should have knowledge on which region of the spectrum represents the component of interest. Therefore, the right-hand side image in this slide, which shows the model, is a result of multiple linear regression statistical technique applied by selecting the appropriate spectral peaks representing the sample interest or the component of interest based on the pre-processed near-infrared spectra, which is again given on the left-hand side bottom image. As you can see from the image on the right-hand side, the regression model of the pre-processed near-infrared spectra resulted in a correlation coefficient of 0.99987, which is actually closer to 1, with an error of 0.07, which is in fact less than 0.1%. So when this model is applied for predicting the analyte or the component of interest during a manufacturing process, it will result in less than 0.1 error with an accuracy of 99%. And that's really good. So you should remember that similar models can be built for any sample, considering that appropriate spectroscopic techniques are used depending on what measurements are needed and the chemical and physical properties of the sample and the investigation. So moving on to the next slide, slide 36. The images in this slide 36 are an example for detecting moisture content in a powdered chemical during a manufacturing process. The top image on the left-hand side is mathematically processed near-infrared spectra of the powdered chemical acquired at various time intervals during a production process. And the bottom image on the left-hand side shows the moisture content observed in the same powdered chemical during real-time production process. As you can see in the bottom left-hand side figure, the amount of moisture keeps increasing until the time point 1 hour and 20 minutes, which is not so clear, as you can see, and starts to decrease beyond this time point. So the increase in the moisture content until the time point 1 hour and 20 minutes is as a result of addition of a chemical solvent to the process reactor, and the decrease in the moisture level after 1 hour and 20 minutes is due to the drying process, which was actually initiated at this time limit. The real-time measurement of moisture during the manufacturing process was programmed based on the regression model built from the top left-hand side image by selecting the spectral peaks representing the water molecule. And to be more specific, the spectral peaks around 1400 and 1900 nanometer region are characteristics of the absorption bands corresponding to the oxygen and hydrogen bonds present in water. Right now, I can sense that some of you are about to max out from the model building process and the chemometric procedures. So before you're exhausted, I would like to show you a schematic representation of how our real-time reporting works during a production process. So in this slide 37, you can see an elaborate scheme of how we acquire spectra from a sample, which is under production within a blender, which is highlighted on the bottom left-hand side of the slide, which is in blue color. Our portable spectrometer can be mounted on the V-shaped blender with its spectrometer probe inserted into it after customization. So prior to mounting the spectrometer to the blender, so like the one shown in this slide, the spectral data for known standards is acquired initially in order to build a model by selecting the moisture peaks using the Chemometrics software. So once the model is built, it can be transferred to the portable spectrometer in order to monitor the moisture content in the sample in real time while the blender is still under operation. And the mounted portable spectrometer can be controlled using an external computer or a laptop, which is pictorially represented as the analyzer control in the top left-hand side of slide 37. And when using this analyzer control, the spectral information on the sample within the blender can be acquired and pre-processed before the moisture content is predicted using the model built initially from the known standards prior to the production process. And the predicted results are immediately reported, thereby allowing the operator or the spectroscopist to control the process in real time in case if the expected results turn out to be negative. And the real advantage of real-time moisture prediction helps in saving conventional moisture analysis time and laboratory space, therefore resulting in quick marketing of products. And moreover, our spectrometers can be connected to the production process line and controlled by various means which can be wired as well as using Wi-Fi. And you might ask, what are the capabilities of our portable spectrometer to measure moisture under different conditions? So to answer your questions, the next slide, 38, gives you various situations where the spectrometer can be used. So to begin with, let's talk about the environment. The spectrometer can be used indoors as well as outdoors in both hazardous and non-hazardous conditions, and also at different temperatures. the spectrometer can be customized based on the power requirements and the type of probe required for analysis. Sometimes it becomes, mandatory to use AC or DC powered spectrometer since the industrial applications differ in various circumstances. And also due to design constraints and challenges enforced by the industrial production unit, the spectrometer probe needs to be engineered based on the length, size, and the environmental conditions in order to fit the process line. In addition, the spectrometer can be designed to mount on a production process line with the capability to access it remotely using a wireless connectivity. The two images on this slide shows how a spectrometer is mounted to the production unit, which is shown on the bottom image, and how the spectrometer probe is inserted into the process line on the top image. And some of you might wonder about the maintenance cost for such an advanced spectrometer configuration. So these spectrometers require low maintenance, which is actually shown in slide 39, which include, and the maintenance includes light bulb replacement, which for every 2,000 hours. And this bulb is a source which emits the light in order to analyze or investigate the moisture content in the sample depending on the scattering effect of light. And this scattering effect of light is due to the molecular property of the sample. This is like molecular and vibrational properties of atoms present in the component of interest. The models built using the Chemometrics software have to be validated for different production processes, and it should be calibrated depending on the type of spectrometer used for real-time monitoring. And I guess it's time to end the science and engineering talk and move on to real-life case studies, which can serve as example where the moisture content is measured from the component of interest during production process. And as a heads up, I would like to talk to you about two case studies where the moisture content is measured for two very different industrial processes. So in slide 41, I would like to begin the first case study discussion by presenting a successful method employed to measure moisture in molasses for an animal feed application. So this client reached out to us to help them with quick moisture measurement in their molasses production line. And the goal was to measure moisture content in molasses between 0 and 25% weight-by-weight basis. So this client tried various inline methods to measure moisture, which included conductivity and photometers for many years. But their inline methods did not work out very well since the conductivity measurements varied a lot across various formulations, and the photometer measurements could be calibrated to only one formulation. So after listening to their challenges, we offered them a solution explaining how spectroscopy can allow them to develop global models across different formulations to predict moisture accurately. So before we could install our spectrometer to the manufacturing process line, many limiting factors were taken into account. And some of these main factors were viscosity and air bubbles present within the production pipeline, which is shown on slide 42. The viscosity was very high within the process line, which in fact resulted in spectrometer probe fouling. And this fouling was overcome by customizing our spectrometer probe with a heating element, which increased the product flow around it, therefore greatly reducing the stickiness of molasses over the optical path length of the spectrometer probe head. Secondly, we had to tackle the air bubbles in the manufacturing process. The production process used vacuum in order to dehydrate the molasses. However, the application of vacuum resulted in air bubbles. And it should be noted that each time when an air bubble interferes with the optical path length of the spectrometer probe head, it will result in an error. Therefore, this problem was addressed by turning off the vacuum system in the process line for a couple seconds through the programmable logic controller associated with the customers or the client's manufacturing process system. And this slide shows the picture of our inline optical spectrometer on the right-hand side of the image, attached to a lengthy probe which was inserted into the molasses manufacturing process line. And as soon as these challenges were addressed, spectroscopic measurements were carried out to analyze moisture content in molasses. And after the spectral data was acquired, chemometric analysis was performed. And as you can see in the slide 43, it predicted the moisture content with 4 times more accuracy than the customer's target measurement, that is 0.25% versus their necessary 1%. In addition to moisture measurements, we were also able to predict the protein and fat present in the molasses by building separate chemometric models. So that was the first case study, and now moving on to our second case study. Another customer reached out to us to once again help them with quick moisture measurement in the flower production line. And this customer's certificate of analysis mandates the moisture level of the flower to be 14% weight by weight basis. However, as soon as the flower is manufactured in the facility, the moisture level in it changes. It changed tremendously due to transport and storage. So they had to carry out laboratory-based analysis for moisture measurements frequently in order to keep the moisture level of the flower matching the certificate of analysis. This was not so convenient for them since lab-based measurements were not possible, considering that they had a very high product turnover rate. So in order to overcome this challenge, we once again offered the inline optical spectrometer solution in order to predict the moisture content during flower manufacturing process, in addition to other measurements such as protein and ash values. In this slide, we show some of the installation challenges before we could acquire spectroscopic data on the flower. First, the inlet of the dough mixer was placed at a height of 40 feet above the ground. Hence, we had to customize our spectrometer in order to mount it to the flower hopper at this height. In this case, the height was not an issue in order to access the spectrometer, since it had the capability of connecting to the PLC, which is programmable logic controller, using Wi-Fi connectivity. Prior to carrying out any spectral measurements, the flower hopper had to be calibrated in order to accommodate tight packing fraction from 1.5 tons of product within the hopper. And the entire process was actually automated through a system-controlled PLC. So as soon as these calibrations were over, spectral measurements were acquired in real time at 10 milliseconds to determine the water addition to the dough mixing process, and the results were actually shown in the next slide 46. As I mentioned in one of the few slides back, a model was initially built with known moisture content in the flower prior to conducting inline spectroscopic analysis in real time to measure the moisture. This model resulted in an error less than 0.2% with a correlation coefficient of 98%, which is shown in the image here. The model worked very well in predicting the moisture content of the flower, which was within the flower hopper in real time, and the prediction accuracy was 0.2%. The error was 0.2%. And in addition, we also predicted the protein and ash content in the process line by building specific models for each. Our model was used for nearly 4 months without the need to adjust the model parameters, which was really good. And that would be the end of our 2 case studies, and I hope you all would have got a clear idea on using our spectroscopic solutions to measure moisture in industrial process. And before we take any questions, here are some of the highlights to summarize our overall presentation. The optical spectrometers have a faster acquisition time, which is in the range of milliseconds. Therefore, it can be used to optimize reaction processes, which are very, very fast. And this capability of faster acquisition time enables the spectroscopist or the user to take real-time measurements of the component of interest, therefore minimizing product waste and saving time from doing lengthy or time-consumable laboratory-based analysis like Karl Fischer, loss on drying, conductivity, photometer, or microwave, etc. In addition, the inline real-time measurements help to validate the consistency of the product quality with increased yield. And most importantly, since the inline spectroscopy solutions reduces the downtime for lengthy lab-based analysis, it results in less holding time for distribution of finished product for marketing. So that would be the end of my session, as well as the overall presentation. And once again, thank you for attending this webinar. And with that, we would be happy to answer your questions.
Okay. So if you have a question, again, a reminder, please type it in to the bottom right. While people are filling in the questions, there were a couple of questions that came in from the first section, and Navin, I think you're the appropriate person to answer this. The first question is, what is the limit of detection with spectroscopy for moisture measurement?
All right. So there are two similar questions. The first question is, what is the limit of detection for water in the process? And what is the range of application, which is like percentage moisture content, weight-based for spectroscopy? In order to measure moisture, near-infrared spectroscopy is the best bet because near-infrared spectrum can absorb water bands and can give distinctive peaks at 1400 and 1900 nanometer region. And the limit of detection for near-infrared spectrometer for water is up to 1% or 10,000 ppm, which is like vice versa. 10,000 ppm is 1%.
Okay. The second question, what is the range of application, the percent moisture content wet base for spectroscopy?
Oh yeah, so that answers my that question answers my previous response. The range of application is 1% moisture. So any moisture content that goes below 1% cannot be measured using near-infrared spectroscopy. And again, 1% is equivalent to 10,000 ppm.
Okay. What is the spectral range of the reveal?
Okay, so there are different types of reveal instruments, reveal spectrometers. The different types are UV visible, near-infrared spectrometers. For UV and UV visible, the spectral range is between 200 to 800 nanometer. And for near-infrared spectroscopy, reveal near-infrared spectroscopy, the range is between 1100 nanometers to 2100 nanometers.
This question will be for Stacey. What are different ways to clean a fouled probe without removing it from the process?
So there are a couple ways to clean a fouled probe. One is you can actually install, if you recall back in several slides, then you can actually like insert the probe and then have like another thing inserted that points directly at the gap that cleans it. There are also basically automated retractors. That's the word I'm looking for. Sorry, automated retractors that you install your probe into. It inserts the probe during the measurements, and then when you need to either clean it or you want to run it through a calibration or something like this, then it will retract it, clean it through however many different solvents you want, and then put it back into your pipeline. And this is often used for things like pH probes, but you can use it for optical immersion probes as well.
Okay, next question. Do all spectroscopic methods require labor-intensive models to operate?
So, no, they don't. I mean, there are some analyses that are so incredibly simple that, you can just say, hey, we have this level of signal, it corresponds to this, but it comes when you have a complicated matrix. Water in flour or something like that has a very complex spectral signature. So in order to get the water bands out of that, you actually do need to run a model in order to do this. Now, some models will be more comprehensive than others because there may be, 100 analytes that you have to pull out, and some of them you only really have to work with 2. So it really just depends on your matrix. Navin, do you have anything to add to that?
Yes. So again, the spectroscopic methods do not require labor-intensive models to operate, and it only requires the spectroscopist or the operator to know which mathematical pre-processing method to use in order to build a successful chemometric model.
Okay. Next question is, can you measure more than one thing, more than one constituent?
Absolutely, yes. We can measure more than one constituent, and the maximum number of constituents that can be measured is 12, considering that the spectral peaks for each constituent do not overlap each other.
Okay, and then there was a question came in regard to the case studies that you went over, Navin. Is this data from single fiber used?
So there are various probes used for different applications, and in this case, I think it is a single fiber with one measurement probe, and the other one was the reference head, as far as I recollect.
Okay, another question is, in your experience, how much time or money have you saved by moving to one of these inline solutions?
So, go ahead, Stacey.
I was actually going to pass it to you because you probably actually have a little more experience in this, Navin. So.
All right, I think so, yeah. So from my experience, of course, more time can be saved by using an inline spectroscopic instrument when it is incorporated into a manufacturing process line. And this time includes, substantial time spent in the lab to analyze or test the product. And while we wait on the results, we lose, more time which can be used for shipping and marketing. And let's say that if you want to do a Karl Fischer titration in the lab, you stop the process, you get the sample out, and then you take the sample to the lab, which again takes more time. And you need to get laboratory space first. And once you get the laboratory space, you need to find an available instrument to do it, which is Karl Fischer in this case. And as soon as you start the procedure, you wait on getting the results, and this includes solvent waste and other chemical waste that are needed to do this. Instead of going through all these hassles, inline spectroscopy instruments can give you immediate results in order of few seconds. And you can compare the time taken for doing the Karl Fischer titration, which takes like more time, and you can contemplate on deciding how soon the inline spectroscopic methods can help you to market faster than you do in the laboratory-based analysis time.
Okay. Okay, thank you. So we are finished with the Q&A. We have a couple of Q&A that have come in that seem really specific to their applications. So I think we'll reach out to them and address them offline. But at this point, Michaela, I'm going to turn it back to you, and thank you very much for attending our webinar.
Great. Thank you, Krista, and all the presenters. Just want to remind everyone that ISA's Process Control and Safety Symposium and Exhibition is coming up in just a week and a half, 2 weeks. It's coming up the 7th through the 10th of November in Houston, Texas. Registration is still open, so I would suggest going to isa.org/PCS2016 and registering. Stacey will be there. She's giving a presentation Tuesday morning, So please stop by her presentation, say hello, and it'd be great to have you. We also, coming up in 2017, mark your calendars for ISA's Analyst Division Symposium. That's in Pasadena, California, April 23rd through the 27th. So mark your calendars for that. Call for papers is open for that symposium. We did record this webinar, so if you missed any portion of it or if you wanted to share this webinar with your colleagues, I will be sending a link to the recording, hopefully this afternoon, if not by tomorrow, so all of you can watch this webinar. A survey will pop up in your browser. Take a moment or so just to fill it out. Let us know how today's webinar went for you. And we appreciate you staying with us today and listening to our webinar. We hope to hear from you soon and join us in a future webinar.